In this video, we will be talking about section 6.3, areas under any normal curve. Our goal is to find a z-score from a given normal probability using the inverse normal probability distribution. In section 6.2, we learned that the normal CDF function on our calculators lets us find the area under a normal curve. So let me review what that looks like. A normal curve is sort of bell-shaped, and remember that the area underneath this curve, between this curve and the x-axis, the total area is 1 for every normal curve. If we had a normal curve where we knew the mean was, say, 75, and we knew the standard deviation was, I don't know, say 5, then we always do 3 standard deviations above and 3 below. So this would be 80, 85, 90, 70, 65, 60. And let's say these represent test scores, and I wanted to know the probability that a randomly selected person scored above a 82. What I would do is use the normal CDF function on the calculator, where I put in the lower bound, which 82 is about right here, and we're finding the area right here from 82 and up. So my lower bound would be 82, and this normal curve, remember that it goes forever. It never ever touches the x-axis. So we do from 82 to infinity, and then we put the mean, which was 75, and the standard deviation 5, and that gives us about 0.0808, which is about an 8% chance that a randomly selected person scored above an 82. But what we actually found is the area of that shaded region. 0.0808 is the area of that shaded region. And that's for a regular normal distribution. So this is a normal distribution. But remember that a standard normal distribution has that same bell curve shape, but for every standard normal distribution, the mean is 0 and the standard deviation is 1. So this would be 1, 2, 3, -1, -2, and -3. So in this one, we would be finding the probability that the z-score is in some region. So say I wanted the probability that z is less than, we'll say, 0.4. So 0.4 is about right here. And we'd be finding, since it was less than this time, we'd be finding that area to the left. And so we would do norm CDF, and our lower boundary this time is negative infinity. Our upper boundary is 0.4, and then we would do the mean, which is 0 because it's the standard normal, and the standard deviation 1. And that gives you about 0.6554, which is the area of this shaded region. So that's a bit of a review of what we did last time. We were given either the x value or the z value if it was a standard normal, and then finding the area under part of the normal curve. Now we're going to do that process in reverse. So now we're going to know the area and want to find the z or x value that corresponds to a specific area. For this, we're going to use the inverse normal function on our calculators. However, our calculators can only work from the area to the left of a given value, so we'll have to do a bit of problem solving at times. So for the inverse normal on the calculator, you're going to press Menu, and then you're going to press Statistics, and then you're going to press Distributions. Same place we've found all the other things we've been using lately. And then you'll find inverse normal. And it's going to ask you for the area right here. That's the first thing. And then it will have mu and the standard deviation. And if it's a standard normal, those will be 0 and 1, or they could be the mean and standard deviations of the population. Let's take a look at an example. Find the z-value such that 65% of the area under the standard normal curve lies to the left of z. So I'm going to draw a standard normal curve. Since it's a standard normal curve, the mean is 0, the standard deviation is 1. And we want to find the z-value such that 65%, I'm kind of guessing that maybe somewhere around here, of the area is to the left of z. So we want to know what is that z-value where 65% of the area is to the left. And so the area of that region is going to be 0.65. So we're going to choose inverse normal on our calculators. We're going to plug in the area on the left-hand side, and it always needs to be the area to the left of that value. That's the only thing the calculator will accept. So we're going to put 0.65, and it's standard normal, so the mean is 0, the standard deviation is 1. And when you plug that into your calculator, you get 0.3853, which is the z-value where 65% of the data falls below. We could also call that the 65th percentile. The 65th percentile is the number where 65% of the data falls below. Here's another example. Find the z-value such that 42% of the area under the standard normal curve lies to the right of z. Again, we have a standard normal curve, so that tells us that our mean is 0 and our standard deviation is 1. And 42% of the data is to the right of z. So we're trying to find z so that this part right here is 42% of the data, or the area of that part would be 0.42. But the problem is the calculator will only accept the area on the left. So I need this area over here. So I need to manipulate my numbers a little bit. If I know that 42% is above, what percent would be below that z-value? So I can just subtract 100% minus 42%, and I get 58%. So this part right here is going to be 58% of the data values, or an area of 0.58. And that's the number that I need to plug in for the area when I use the inverse normal function. So inverse normal on the calculator, we put in the area, 0.58. It's standard normal, so mu is 0, standard deviation is 1, and we get 0.2019. And so that would be the z-value where 42% of the data values are above, or 58% are below. Number 3, a large set of test scores at a local college follows a normal distribution with mu equal to 82 and standard deviation equal to 4.5. So this time we have a normal distribution, but it doesn't say standard normal. It's just a regular normal distribution, so we're not using mu equals 0 and standard deviation equals 1. This time we're going with our original values where mu is 82 and the standard deviation is 4.5. What score represents the 25th percentile? The 25th percentile is the number where 25% of the data falls below. So the area of this part right here would be 0.25. And we want to know what is that x value in this case. So I'm going to do the same thing, inverse normal. And I put in the area of 0.25, the area on the left-hand side. And I can put in my actual mean and standard deviation. 82 is the mean, the standard deviation is 4.5. And that gives you x equals 78.9648. So instead of getting a z-score, like we did with the standard normal distribution, we get the actual x-score. So let's say, so these are test scores at a college, the mean is 82. If you scored a 78.9%, you did better than 25% of your classmates. That's what the 25th percentile means. A person with what score did worse than 30% of the population? If you did worse than 32% of the population, that means you did better than 70% of the population, which is the 70th percentile. So remember, a percentile is the number or the percent of people who did worse than you or are lower than you. So the 70th percentile maybe would be somewhere up here where this part is 70% or an area of 0.7. And this part right here would be 30% or 0.3. But again, the calculator needs us to enter the part on the left. So in the calculator, we are going to type in inverse norm, and we will put 0.7, the area to the left. The mean is 82, the standard deviation is 4.5, and we get x is equal to 84.3598. So the person who scored in the 70th percentile got about an 84%. And they did better than 70% of their classmates, worse than 30% of their classmates.